Hey guys, welcome back to Agora Math Circle's Mathcounts training. Now, this is session 7 of a 12-part series, so if you haven't watched the other videos, go ahead and watch those, and once you're done with that, come back to this video. My name is Mugil Shanmugam, and I'm going to be presenting all these videos. Right, so let's get right into the session 7 material that we'll be learning today. Okay, so what exactly are we going to be learning today? Session 7. So we're going to be covering the following broad topics: last digit and remainder, number bases, special numbers, and Diophantine equations. So these are just types of problems you will see on Mathcounts, and we'll be going over how you can solve each of these problem types. Now, we have some subtopics of this. So in last digit and remainder, we're going to be learning some basic theorems that will help us in solving some sum problems. In number bases, we're going to be learning how to convert between bases and the power of some bases, and we'll also learn some sum problems, so look how we can solve them. Special numbers, we're going to be learning the definition of palindromes and rising falling numbers, two types of numbers, and we're also going to go over sum problems. And finally, we're going to be doing Diophantine equations, and we'll be learning some basic principles based on algebra and sum problems. Okay, so let's get right into it. So here's our warm problem, and this is based on something we learned in session 6. So if you watch that video, you should be able to solve this one. So here's the problem. If 9 is congruent to 4 mod 5, and this is true, does 81 is congruent to 16 mod 5 hold true too? Simplify the new statement first before making your conclusion. So you could use a theorem to solve this, so in that case you don't have to simplify. Otherwise you can simplify and you can solve it that way. But either way, verify whether this is true or whether it's not true. So go ahead, pause the video, and solve this problem. Okay, so hopefully you pause the video and you solve this problem, so let's go over the answer for this one. Okay, so we can simplify this to 81 is congruent to 1 mod 5. Why? Well, 16 divided by 5 gives a remainder of 1, and 81 divided by 5 gives a remainder of 1. That's how we get 81 is congruent to 1 mod 5. Now, we can verify this is true manually, right? Because 81 divided by 5 gives a remainder of 1, and 1 divided by 5 gives a remainder of 1. So, as I said here, you can verify this by simplifying and checking manually. However, we could have also known this statement was true by using the theorem 3 of modular arithmetic, the modular exponentiation theorem. So this theorem says that if a is congruent to b mod m, then a to the power k is congruent to b to the power k mod m. So basically, if you look carefully here, you would have seen that we rose 9 to the second power to get 81. So 9 squared is 81. 4 squared is 16. Yeah, 4 squared is 16. So that's how we got this new statement, and it has to hold true because of that theorem that we learned before. Okay. So now so your answer for that one was yes, this is true. Okay, so let's move on to our first topic, which is remainder and last digit. So the first term we're going to learn is Fermat's little theorem, and it states that given a prime p and a is not divisible by this p, then a to the power p minus 1 is congruent to 1 mod p. So what this is saying is when a to the power p minus 1 is divided by p, you're going to get a remainder of 1. That's all it's basically saying. Now, if we're asked to find the last digit or the unit digit of a number to a high power, so they'll give you like 4 to the power 6,500. What's the last digit of this? So obviously, you could sit there by hand and calculate this out, but it'd be way too hard and way too tedious, right? So what you would do instead is you'd break it up into this form, 4k plus r. So 4 into some number plus r, which is another number. So when you break down your bigger power into this, then you can simplify it to simply a to the power r, because these two are congruent when they're divided by 10. Basically, this is saying that when a to the power r is divided by 10, you're going to get this remainder, a to the power r, right? A to the power r is your remainder here. You're going to get the same remainder over here when you do it with this. And your remainder here is going to be your last digit. So what it's saying is basically you can break this down into a to the power r. Similarly, if you're asked to find the last two digits, it's 40k plus r, and you're going to do mod 100. And then the last three digits, it's going to be 400k plus r, but you're still going to be doing mod 100. Either way, all this is really saying is you're going to be breaking it down, right? If you have a bigger power, you're going to be breaking it down into this form, so you can simplify it to simply a to the power r, and then based on that, you can calculate a to the power r mod 100 or mod 10, and you find your last digit, last two digits, last three digits, and so on. Okay, so now we have also Euler's theorem, sorry for pronouncing that wrong. So if a and n are relatively prime, so they have no other common factor other than 1, right? Then a to the power phi n is congruent to 1 mod n. And here, phi n is the number of positive integers that are less than and relatively prime with n. Okay, so we know what relatively prime is. But here, phi n, this is just a Greek letter, and phi n is just going to be an expression, and you're going to get a number for phi n. N, you're just going to plug in your number, and based on that, you can plug into a formula we have, and I'll go over that formula in a second. But phi here is just a Greek letter. So a to the power of phi n is congruent to 1 mod n. So when you divide by n, you divide this a to the power of phi n by n, then you get a remainder of 1. So first, n here, you're going to break it down into this form, right? And you may remember this if you watched the previous video. This is basically just a prime factorization. P1 is the first prime, and how much ever of that you have, that's your power. And similarly, P2, P3, and so on until you get your last prime number to the power m. Now, this is how we broke it down into prime factorization. Now, the formula for phi, so phi of this n is going to be the first prime to the power a minus the first prime to the power a minus 1 into the second prime to the power b minus the second prime to the power b minus 1, all the way until you get to the kth prime, or the last prime you have, which is going to be the power m minus the last prime to the power m minus 1. Now, how do we find this a, b, and m? Well, when you prime factorize, based on how much of this prime 1, prime 2, and prime 3 you have, based on that, that's how you're going to fill in your a. So if I had two 2's when I was prime factorizing, then I would get 2 to the power 2. So my a was going to be 2. And based on that, I can fill out the rest of the formula. So here I've done a little example. Let's just say that they ask you to find phi n, right? So this symbol and then n in parentheses, like right here. So 10, when we break it down, it's simply 2 to the power 1 times phi to the power 1. That's its prime factorization, right? So then we can plug it into this formula. 2 to the power 1 minus 2 to the power 0, because that's what the formula says. And similarly, 5 to the power 1 minus 5 to the power 0, because that's what the formula says. And we get 1 into 4, which is 4. So this is our power. This is what we'd write up here if we were solving this out using Euler's theorem. Okay, so yeah, that's just a simple theorem that we can use to solve. Okay, so now let's do the same problem. So what is the units digit of 13 to the power 2003? And this is from the 2003 AMC 10. So obviously here, you're not going to calculate it out by doing 13 times 13 times 13, 2003 times. That's not going to work. You're going to have to use this formula we learned back here on how you can find the last digit and unit digit of a number to a high power. You have to break it down into this form. So go ahead and try to solve this one, and then I'll go over the answer. Go ahead and pause it. Okay, so hopefully you solved the video. You solved the problem. So now let's get back to the video. I'll go over the solution to this problem. Okay, so first, use our formula to break this down into smaller modulo, right? We don't want to solve out 13 to the power 2003. That's way too much work. What we're going to do instead is we're going to break it down. So the first thing we're going to be doing is 13 to the power 2003. We're going to get the same last digit as if we did 3 to the power 2003. So either way, we're going to get the same remainder when dividing by 10. They have the same last digit. So we can break it down into 3 to the power 2003. That's much easier, I would say. And then here, now we have 3 to the power 2003. While this is easier than 13 to that same power, it's still way too much work. So now we have to break it down using our form. So our form here was 4k plus r. So we could break this down into 4 times 500. So 4 times k. Here k is 500. And 3 to the power 3. 3 is your r. So remember, we just broke this down into this form. And then what did they say back here? They said it's simply just equal to this r. So now what we figured out was this whole huge expression, 13 to the power 2003, is just going to be equal, or is congruent to 27 mod 10. Now we just need to figure out what 27 mod 10 is, because 27 is 3 to the power 3. Now we just need to figure out what is 27 mod 10. Well, 27 mod 10 is just 7, right? Because 27 divided by 10, you'll get a remainder of 7. That's how we find that 7 is the units digit of 13 to the power 2003. Okay, so that's how we just solved our first problem. And as you can see, it wasn't that hard. All we need to do was break it down accordingly. Okay, so now we're going to move on to number bases. So generally, you're used to numbers written as just 312 or 212. But usually, they're written in decimal form. You can also write these numbers in different bases, and that would change their value as you see it. They would still have the same value in the decimal form or base 10 form, but they would be different numbers in different bases. So, by different numbers, I mean to say they'd be represented differently. So let's go ahead and see how we can do all that. So any rational number can be written like this, when all the a values are between 0 and p minus 1, both m and n are positive integers, and p is the base. So here, p's are base, like base 10, then you just plug in 10 for all these, right? And so a subscript n, so this is like your first a value, your last a value, your second to last a value until you get to your first a value, and then this is like your a to the your negative 1th value, your negative nth value. And here, as you can see, we're multiplying it by p to the power n, p to the power n minus 1, and so on until we get to p to the power minus n. So this is for more decimal numbers. That's why you'd be using a to the power negative 1. So here, let's just say that if you had like any number after the decimal point, then you would use p to the power negative 1 and a to the power negative 1, these terms. But any positive integer, you can express it, but you don't need all these negative terms because there's no numbers after the decimal point, right? So you can write it as a subscript n, p to the power n, plus a subscript n minus 1, p to the power n minus 1, all the way until you get to the first a value into the power into 1, basically, because p to the power 0 is just 1. So as you can see here, this one is more used with decimals, or because you have some numbers after the decimal point. That's why you need these negative values here. But then here, or not negative values, negative powers, and here you're just using a positive integer, so you don't need all those negative values. But yeah, those are just two basic formulas you can break down your numbers into. Okay, so here's an example. 4, 3, 2, 1, expanded in base 10. Well, first we find our first digit, basically. 4 times 10 to the power 3. So what we're going to do is we're going to multiply it by our base to the power 3. So here, basically here, a to the power, a subscript n and everything, these are just digits. So a to the subscript n is a digit, a subscript n minus 1 is a digit, and so on until we get to our decimal digits when we get these. But anyway, as I was saying, right, 4 is going to be multiplied by 10 power 3. Why? Because 10 is our base, and you can count 1, 2, 3. So it's going to multiply by 10 to the power 3. Or you could count it as the number of digits minus 1, right? But it's more simple just to go 1, 2, 3, then I get to 4. So it's going to be multiplied by 10 to the power 3. Plus 3 times 10 to the power 2, right? And then 2 times 10 to the power 1 times 1 times 10 to the power 0. So that's how we broke this down by using our base and the different digits we have. Remember, your last digit should always be multiplied by the base to the power 0. So arrange the others so that you get to that last 10 to the power 0. Now when we have 4, 3, 2, 1 expanded in base 8, well, if this number was written in base 8, all we had to do is the same thing, except we're going to be switching everything with an 8 instead over here, right? The reason is because we're using base 8, but the same powers you can see and the same digits. Similarly, in base 5, we're swapping everything for a 5 at the bottom, or as our base. However, the powers are always the same and the digits are always the same. So that's just how you can expand these numbers in different bases, based on what base they're given in. So make sure to check that when you're given a problem, right? Generally, they will specify it's in base 10 or it's in base 4 if the problem is related to converting between bases. Okay, so now let's see how we can convert from base 10 to other bases. So base 10 is your ordinary numbers that you see every day, but sometimes you'll be asked to convert to other bases. So method 1 is division method. So convert 497 from base 10 to base 5. So the first thing we do is we find the power of 5 that is the smallest but least away from 497. So what is the power of 5 that is closest to 497 but not greater than it? Well, in this case, it's 125. 625 is greater than this, but 125 is not, so 125 satisfies our conditions. And this is 5 to the power 3. Now, so we know that this is going to be 5 to the power 3, and our number is greater than 5 to the power 3. So if we saw back here, 5 to the power 3 went with the 4th digit, a 4-digit number. So that's how we know that this is going to be a 4-digit number. Because it was 5 to the power 3, we know there's going to be 4 digits. So based on that, you can figure out how many digits there are in our numbers. Now, the first thing we're going to do is we're going to divide this by 5 to the power 3. And what do we get? 3 remainder 122. Don't convert it to a decimal, just keep it as 3 remainder 122. Now what we're going to do is we're going to divide 122 by 5 to the power 2, which is 25. And we get 4 remainder 22. Now divide 22 by 5 to the power 1, which is just 5, and we get 4 remainder 2. So we can rewrite our number as 3,442, because remember 3, 4, 4, 2. This is how we got all the digits that make it up. And at the bottom you write a little 5 to show that this is in base 5. If you don't have anything there, it's generally in base 10 or in base 10, our normal form. But that's how we convert. We're just going to be dividing repeatedly and then finding a remainder. Now, let's just say here, instead of 122, I had 24. Well, instead of dividing 24 by 25, I just put a 0 here and move on to my next power of 5. In that way, I don't have to deal with any decimals, and that's just how you do it. You just put a 0 there if it's not divisible by that particular number. By not divisible, I mean it's smaller than your divisor. Okay, so here's an expansion method. So here we were converting from base 10 to other bases. Now I want to convert from another base to base 10. That's obviously something you're probably going to be asked to do. So here I have 1342 base 5 to base 10. So this was pretty simple. I think we already went over this a little, but what we do is we take our first digit, multiply by 5 to the power 3, because we have 1, 2, 3, 4 digits, so you multiply by 5 to the power 3, and you keep going, each digit multiplied by a different power of 5 until you get to 5 to the power 0. And when we calculate this all out using PEMDAS, we get 222. So that one is pretty simple. You just have to expand it and multiply. Now, to convert between two random bases. So this is for converting from base 10 to other bases, and this is from another base to base 10. But what if I want to convert between two random bases? Well, first I convert from base B to base 10 using expansion, so I do this, and then I convert from base 10 to base C using division. So I go back and do this method to get my final answer. So we'll go over a sample problem using that, but this is just how you can convert if you need to expand, if you want to convert, and so on. Okay, so here's a sample problem. Express the following in base 3. 312 base 4. So here you're going to have to convert your 312 base 4 into base 10, and then from base 10 convert it into base 3. So go ahead, pause the video, and try to solve this problem. Okay, so hopefully you solved the problem. Let's go over the answer. So first convert from base 4 to base 10, right? You have 312 base 4, so we're going to expand it. Here we have 3 digits, so the first thing we're going to multiply is 4 to the power 2. 3 times 4 to the power 2, plus 1 times 4 to the power 1, plus 2 times 4 to the power 0, and we get 54. Now convert from base 10 to base 3. So we have 54 as our base 10 number. So what are we going to divide by? Well, the greatest power of 3 that is not greater than 54 is 27. So when I do 54 divided by 27, I get 2 remainder 0. So I get a clean 2. So then I have to do 0 divided by 3 power 2, which is 9. 0 divided by 9, I don't have anything there. And then when I also do, now I divide by 3. 0 divided by 3, I would not have anything there either. I would just get a 0. So when we fill out 0 for division by 9, 3, and 0, right? And then 3 to the power 0, I said 0 here, there should have been 1. So when I divide by 9, 3, and 1, I get 3 zeros. So that's how I get 2,000 as my answer. 2, and then the 3 zeros we got by dividing by 9, 3, and 1. Not 0, 1. But that's how we get our answer, which is 2,000. Okay, so now let's move on to some special numbers. So special numbers are just different numbers that have some quality that makes them special. So palindromes are one type. Palindromes are numbers that are the same, whether they're written forward or backward. So examples, not exams, examples are 101 and 121. For example, 101, right? 101, if I write it forward or backwards, it's the same thing. Same way, 121, if I write it forward or backwards, it's the same thing. Palindrome prime numbers or numbers that are palindromes and also have no other factors than 1 in itself. An example of a Paul prime, as I call them, are 191 and 757. So these are prime numbers that are also palindromes. Now, a palindrome square number is a palindrome that is also a square sum number. So 4, if you write 4 backwards or forwards, or 94,249 forward or backwards, you're going to get the same thing. and these are also square numbers. So based on that, we got these palindrome square numbers. Now, the number of palindromes with n digits we find by using two different formulas based on if n is odd or n is even. So if I want 3 digits, I'm going to use this formula, but if I want 4 digits, I'm going to use this formula. For odd, it's going to be 9 times 10 to the power n minus 1, that was a minus over there, over 2. And here it's 9 times 10 to the power n minus 2 over 2. So if it's odd, it's going to be n minus 1. If it's even, it's going to be n minus 2. So based on that, you should be able to remember the formulas, and you can apply them to find the number of palindromes with a number of digits. Okay, so here we have rising and falling numbers. So rising numbers have digits that are larger than those on the left, like 1, 2, 3, 4, 5, 6. If you had a number with all those digits, and they were ordered like that, that's your rising number. Falling numbers would be like 6, 5, 4, 3, 2, 1. If the digits are falling like that in the number, then they're falling numbers. In other words, rising numbers have digits in increasing order, and falling numbers have digits in decreasing order. So the number of rising numbers can be found with 9 factorial over n factorial into n minus 1 factorial. You may recognize this as 9 choose n, right? You could have written this as a combination. I just wrote that in factorial form here. But what this is saying is n here is just going to be your number of digits. So if I want a 3-digit, all the 3-digit numbers that are rising numbers, and I could use this formula, plugging in 3. And the number of falling numbers is going to be 10 factorial over n factorial into n minus 1 factorial, which is the same as 10 choose n. And again, n is my number of digits, like the number of digit numbers that I want. So like 4-digit numbers, then I can plug in here for n. Okay, so those are just 2 more quick formulas we can use for rising and falling numbers. So here's a SAM problem. How many decreasing numbers are there between 100 and 500? So be careful about this one. 100 and 999, you could just use the formula straight. Here, however, you're going to have to do some subtraction at the end, or you may need to change your formula, so you only get the numbers between 100 and 500 that are decreasing. Decreasing numbers are the same as falling numbers. So go ahead, pause the video, and let's solve this problem. Okay, so hopefully you pause the video and you solve this problem. Let's go over the answer for this one. So we cannot use the numbers 5, 6, 7, 8, or 9 as the first digit, right? Because then it would be over 500. So this leaves us with only 4, 3, 2, and 1, or 0 as our possible first numbers in our in our 3-digit numbers that we're going to find. Now we can plug into our formula. Our formula is generally for 10 possibilities, but since we have 5 possibilities here and n is equal to 3, our formula becomes, so n is equal to 3 here because we're trying to find 3-digit numbers. Between 100 and 500, they're 3-digit numbers, right? So based on that, we can do 5 choose 3, or you could have just written out in factorial form, 5 factorial over 3 factorial into 3 minus 1 factorial. When we cancel that out, you would have got 20 over 2, which is 10. So we find that this is 10. There are 10 decreasing numbers between 100 and 500. This is an example of how in Mathcounts you're going to have to adapt the formula or change the formula so you can use it for a different scenario than where it was originally intended. So originally this formula for falling numbers, it was intended for the whole scope, right? Like 100 to 999. Then you could just use this formula. However, because we only wanted 100 to 500, we had to change this formula and make it smaller in scope so we could have solved. And our answer for this one was 10. Okay, so finally we're going to go over Diophantine equations. So if there are more variables or unknowns than equations given, then there are infinite solutions. So this is kind of like systems of equations, right? If you're given 3 equations, but you have 4 unknown variables, you won't be able to find, there are infinite solutions. You may be able to find 1 or 2, but there are infinite total solutions. In Diophantine's equations, we restrict these unknowns or our variables to integers so we can find finite solutions. Principle 1 of Diophantine equations is just going to be how they're written out. A basic Diophantine equation is of the form ax plus by is equal to c. You may recognize this as standard form. All the terms here are integers because this is a Diophantine equation. Normally in standard form they are also integers, but in linear equations they don't have to be integers. Here what we're going to be doing is we're going to be restricting them to integers so we can solve this and actually get finite solutions rather than infinite solutions. Now, all the terms are integers and a and b have a common divisor d. So a and b can both be divided by this number d. If d does not divide c, then there are no integer solutions. Obviously, there will be decimal solutions or fraction solutions. However, or they could be decimal and fraction solutions. However, since D does not divide C, there'll be no integer solutions. And here in Diophantine equations, or Diophantine equations, we're going to be trying to solve for integer solutions only, because we want finite solutions. If D does divide C, then the general solution we have is, so x0 here is going to be our first solution, and y0 here is our first solution, and then we're going to be plus, or we're going to be adding b times t, t is an integer here, over d, and our second y term here is going to be the first y solution minus a times t over d. And this is an ordered pair because, as you know, the answer to a system of equations is given as an ordered pair. So we have an x and y term, an x term here, and a y term here. And the x and y terms here, so x0 and y0 are solutions, and t is an integer. But that's just our principle 1 on how we can find the different solutions that are integers. We're trying to find integer solutions only. Now, principle 2 says that if a and b are relatively prime, so if a and b are relatively prime, the only common divisor is 1. Then there must be integer values of x and y to make ax plus by is equal to 1 true. So basically what they're saying is a and b, if they only have a common divisor of 1, then there must be integer values to make this equation ax plus by equal 1 true. In other words, c is going to be your 1 over here. Now, principle 3 says in the same conditions as above, and if c is an integer, then ax plus by is equal to c must have integer solutions. So even if they're relatively prime and they only have a common divisor of 1, and c is also an integer, then it must have integer solutions. Now, if x is equal to x subscript 0, and y is equal to y subscript 0, and these are solutions to ax plus by is equal to c, then all the solutions to the equation are in the form x is equal to x subscript 0 plus bt, y is equal to y subscript 0 minus at. So this is similar to how we went here when we looked over our solutions. So if we find out the first x solution and the first y solution, then we can find out the rest of the solutions if we know what t and b and a and t are to solve. So all the solutions are going to be based off your x0 and your y0. They all follow the same pattern. Finally, principle 5 says that for equations in the form ax plus by plus cz is equal to d. So now we have an extra variable z. Then if the greatest common factor of a, b, and c called e divides d without a remainder, the equation has integer solutions. So here, what did we say? We said that if d, the common divisor, divides c, we have integer solutions. Here, we're saying if e, the common divisor, divides d, because we have 3 variables, then there is integer solutions. And for this one, what you would probably do is you want to break it down into, you try to cancel out one of the variables, so you're left with only x and y, and then you can solve using Diophantine equations or system of equations. So here's our sample problem of the day for Diophantine equations. So you could solve this as a system of equations too, or you could try doing it using Diophantine equations. So Mr. Bond packages ties in 2 different size boxes. Box X holds 5 ties, and box Y holds 12 shirts. So here I said 5 ties, here I also meant ties, 12 ties. He packages 99 ties using more than 10 boxes. How many boxes of type X did he use? So what this is saying is basically one box is holding 5 ties and the other holds 12 shirts or 12 ties, you could say. Here I just put shirts and ties, it doesn't really matter, you just want the numbers here. He packages 99 shirts or ties using more than 10 boxes. How many boxes of type X did he use? And this is from the book on 20 more problem solving skills for Mathcounts competition. So here you're going to try to set up a system of equations or a Diophantine equation, and based on that you can solve. So go ahead, pause the video, and try to solve this problem. Okay, so hopefully you solved the problem. Let's go over our solution. So our equation can be written as 5x plus 12y is equal to 99, right? Because 5x, so box X holds 5 ties, and box Y is going to hold 12 ties, and we had a total of 99 ties. You could have also made another equation with 10 because he used 10 boxes, and then you could have solved using that for a system of equations, but here we're just going to use Diophantine equations using our one equation. So here we have 5x is equal to 99 minus 12y. We just brought 12y to the other side. Then this is equal to x is equal to 99 minus 12y divided by 5. Now here we can rewrite this. So basically what this is saying is when I divide by 5, I'm getting a remainder of 0. So I've rewritten this as 99 minus 12y is congruent to 0 mod 5. I get no remainder. Now 4 minus 2y, when I do 99 divided by 5, I get 4. So that's how I got my 4 here. Here, when I do 12 divided by 5, I get 2. So that's how I got my minus 2 that I wrote in here. So I changed this to 4 minus 2y, and that's still congruent to 0 mod 5 because I'm dividing by the same number, right? So I get 4 minus 2y is congruent to 0 mod 5. And from here, we can simply solve this. Set 4 minus 2y is equal to 0 because they have a remainder of 0. And we can solve and we get y is equal to 2 and x is equal to 15. So basically we turn this x into 0 mod 5 because there's no remainder, and we simplified, and then we got y is equal to 2. We plugged back in and we got x is equal to 15. So based on that, we found our solution. So basically what this is basically saying is he used 15 boxes of type X. Okay, so that's how we found our solution. Okay guys, thanks for watching. Please like and subscribe if you enjoyed the video. Leave a comment with any questions you may have. And just thank you so much for watching. See you guys in the next video. Bye.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramathcircle.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!